There's no cat. I don't want cat. I can see the window comes up.
There's a general buzz in the air. What does this mean? What does this, there's a general, some of you are sitting appropriately in stupors, but there's a general buzz in the air. That, people are coming around maybe from maybe the flu, peak of the flu is past. It's time to get a haircut. Right? Yeah, we're all. It's time to discuss the classic example. You'll surely have a homework problem on this. On going to the barber shop. Okay? We're going to go to the barber shop. I guess it's the Casper Sweat Barber Shop, the KS Barber Shop. We're going to go to the KS Barber Shop today. And we're going to maybe analyze, like, we've got, maybe they want to get a helper there. Do they need a helper? Do they need a third person? We got two barbers, so we got barber shop. It's in New York, so there's not much room. It's like it's sort of like the A Cafe. People know about the A Cafe, right? This is the K&S barbershop. So unfortunately, it rapidly takes us into continuous time Markov chains, as you hopefully would expect. But anyway, we draw a picture like this. Here's the service space. So this is barbershop. We have two chairs. I could draw chairs better than that, but we have these two chairs. These are. This is going to be a queue. They're servers abstractly. This is Sean and Michael in K&S Barbershop here. So we have two servers, 1 and 2, and we have some waiting space here, and we have customers coming in, and they come in here, and then they get their hair cut, and then they leave. So this is a queuing model. Now, if nothing else, this is worth knowing for the trivia. When somebody says, name a word in the English language with 5 consecutive vowels. 5 consecutive vowels. Right? You're ready. You're ready. You're in business, right? There aren't a whole lot of words with 5 consecutive vowels. But anyway, here's one. So, okay, cue it. Standard thing, maybe it takes, depending on what kind of haircut you want, it might take 15 minutes to get a haircut. So you think, standard thing happens, customers arrive at some rate, there's some space in here, and if there's nobody, if they're not busy, they're going to go right in and have their haircut and be served, and it's going to maybe take about 15 minutes. And if the two barbers are both busy, the customers are going to wait, but maybe there's only room here for 3 spaces, so there's things kind of a tight space, so there's really 3 spaces. And if these spaces are full, then we're going to assume that they are blocked and blocked if full. So there's 3 spaces. And we might even assume that the waiting people here, if they're waiting too long, they may be able to leave, abandon. I mean, they go in and there's no appointments. It's first come, first served. They just come in randomly, and if one of them's free, they go right into service and get their hair cut. And if they're not, they wait. And if there's more than 3 people, they just leave. But if they're sitting here and they're waiting too long, maybe they're going to abandon. So they might abandon or renege. And here they're blocked if it's full. Now, sort of thing you might think of as well, you think of this thing, and to understand how this performs, you think of the rates of various things happen. So maybe this service time, a haircut takes about 15 minutes on average. If for a quick bowl cut might take like 3 minutes, right? Depending on what kind of haircut you want. Total buzz might be also in the 3-minute range, but this, let's say, averages 15 minutes. And if you really want the super duper special thing, it might take a half hour, with attention to all details appropriately. So it could be, it's random. The service times are random, but on average it takes 15 minutes. So, you could think of the rate. They work at 4 per hour. It's supposed to be an HR here. 4 per hour because 15 minutes is on average. So on average, each of them can cut hair at the rate of 4 customers per hour. That's sort of the rate of these. And if they were both busy, they could handle 8 per hour. So sort of like if this was really hot going business and there were just lots and lots of customers, they'd be pumping out customers at 8 per hour, sort of on average. So you could sort of think, well, if the business is going good, we're going to, cut hair at 8 per hour. Maybe we make $20 a haircut. Were you thinking that's looking good? $80 an hour each, $160. It's looking okay. What are we sitting here for? Learning this stuff. We could do this. Okay. Then customers are coming in, and maybe maybe they come in 6 per hour. 6 per hour. Okay, everything looks fine. I mean, they come in 6 per hour, and there's each of the barbers can cut hair at 4 per hour. So together they come in at 6 per hour and they can go out at 8 per hour. So that looks good. If they actually came in, 16 per hour, no problem. I mean, if they came in at 16 per hour, they go out at 8 per hour, but then they're going to just be blocked, right? Because a lot of them aren't going to, it'll just be pumping them out at 8 per hour. So if this were 16, it's just that they're only going to serve 8, so 8 are going to be lost, roughly. Well, you might think about this problem in exactly the way I've formulated it as the first thing you think. If you were actually thinking about such a system, you had some kind of service system like this, you might think, well, this is how long it's going to take. We're going to be able to handle 8 per hour, and then, well, what kind of demand we'd have. And, well, you'd like to have demand, some kind of good demand. It's not clear what exactly you'd want. And you could have any amount as long, because you'd only serve 8, not an issue. And all of this so far is deterministic. You've got a, everything is rate in and sort of rate outs and what's happening in a kind of just on average. The next cut on this, the more refined look, is to realize that, well, they don't all arrive in clockwork. And the service times aren't all the same. And so maybe on average they're 15 minutes, but maybe they actually vary from 3 minutes to a half an hour. And their arrivals come in at random. That people are just coming in off the street when they happen to come in. They don't occur exactly at, every so many per time. So then you think, well, if they come at 6 per hour, and if each one works at 4 per hour, what happens here? I mean, how often are they busy and so forth? And how often are people blocked? So another problem like this would be that I guess is on maybe it's on the exam. There are the 4 computers in the entryway to MUD. It's an analog of the same problem. The 4 computers sit in the entryway. People use those computers for a random amount of time. Then you think, well, so it's a variation of the same problem, right? That people are using each of the computers a random amount of time. People come in through the thing and sometimes, randomly kind of want to use them. Maybe 1 or 2 people will wait. I mean, that business of waiting is a little unclear. If all 4 are busy, people just go away. Some people might wait, so you could kind of have a little queue. You could sort of try to do this. Or you could be thinking about Carlton dining room, and people are coming in and they're kind of randomly, and they're, say, waiting. You think about getting a sandwich there and same kind of things. You have these queuing modes. But an interesting feature here is when you think about what happens here, this would be, with this description, everything would be routine if it was all deterministic. 6 would come in, and if they came in regularly, nobody would wait at all. They would just go through. 6 would come in and they'd go out 8 per hour. If they came in nice and smoothly, they would just go right through here, and they'd be busy 3/4 of the time, right? Because the rate in is 6 and the rate out is 8 total. And that sort of, they'd be busy. Each hour, there'd be 6 there, and they'd be serving 6 per hour instead of 8. So there's kind of 3/4 of the time they'd be busy, and there would never be any waiting. And there would never be any blocking, and there would be no issue, no kind of performance issue, right? On average, there's no performance issue. The interesting part is the randomness is what creates the congestion. If it could be that this is 16 and then there's congestion all the time, but usually the rate in is less than the rate out on average. But then it's the stochastic variation that makes the problem interesting. And so then you want to know what's the probability that if you come in here you're going to have to wait. How long will you have to wait before, on average? What's the distribution of how long you'd wait, or what's the fraction of arrivals that'll be blocked, and so forth. And there are variations of this problem. Now, I guess that to connect this to last class, hopefully it's clear in your mind how this does connect to last class. Last class I was talking about continuous time Markov chains and emphasizing 2 different ways to model continuous time Markov chains. And I was emphasizing when we had continuous time Markov chains that you have a rate view and a semi-Markov process view. And this view had a discrete time Markov chain and a mean holding times, and this view had this rates. And clearly, this is what we're seeing here, very naturally. The problem's all defined, rates in, rates out, everything is naturally in rates. So this is very naturally here, just directly, if you define it. And you'll see all these problems in the book that are like this, whether they're about invariably one of these problems is a barbershop, just like this. So we have rates in, and then we may have something here that would be a rate. That's a little bit unclear how that's been defined, but then there's rates here, so there's a rate of, and so there's traditional things. The notation is the arrival rate is always lambda, and the service rate is mu, sort of standard notation. So arrival rate lambda, service rate mu, but then that's for each server. And then there's, in this instance, there's two servers. So what I'm describing, or what I want to move toward, is the continuous time Markov chain model. And that's a M2 3 plus M model. This is a kind of notation that's used for queuing models. So this is the arrivals. This is the service. So this is the kind of arrival process, the kind of service process, number of servers, and this is number of waiting spaces, right? So number of servers, number of waiting spaces, 2 servers, 3 waiting spaces. And this plus M is a Markovian abandonment. Just using this, these things could be, so you see things like this. When you see MG1Q is Markovian arrival process, general service, one server, and if there's nothing here, it's assumed to be unlimited waiting room. So this is the same thing as this is, might not be here. And if there's no plus M, there's no abandonment. So this part is abandoned. Now the M's, they could be D. If they were D, it would be all deterministic. So there are letters people stick in here for queuing models. The M all means that everything is Markovian. And the Markovian means if it's an arrival process, it's Poisson, and if it's a service time, it's exponential. So all of this is cast in the setting of chapter 5. If it's a random variable and it's Markovian, it's exponential. If it's a counting process, it's Poisson. So the arrival process we assume is Poisson. The service times we assume are exponential. They're all independent and identically distributed and exponential. The times to abandon. So what you assume is that when a customer joins the queue and can't start right away, that the customer has a certain amount of patience, a random amount of patience. The customer will stay for a certain random time before it just leave. We think of that a patience distribution as also being exponential, which means that there's a constant rate at which the customer might tend to abandon. So there's some rate which this would be the arrival rate, the service rate, and say the abandonment rate. So actually, well, there are these two parameters, but these random things, when they're Markovian, are going to have just a single parameter. So it looks just like the deterministic model. Everything's the same as the deterministic model, no extra data, except we interpret the arrival process as a Poisson process. And we interpret the service times as exponential at these rates. And we interpret the times to abandon as exponential at this rate. So it's like if I said here that they lambda here and theta here, some rate. Each customer waiting has a tendency to abandon at rate theta. So what's happening is we're specifying rates in, rates to abandon, rates to complete service, but we're interpreting those rates not as deterministic but as stochastic. And the simplest thing is Markovian, which has no extra parameters. It's just changing from the deterministic model to a stochastic model. You could say, well, the variability is different, but this just puts in some sort of standard variability. So in a way, this is the simplest stochastic model. We just take the same deterministic model and put stochastic treatment about the deterministic rate. So the arrival process is a Poisson process at this rate. Service times are exponential with this rate, and abandonment times are exponential at this rate. Okay. In this case, we're here, and while we have this too, this is, and then out. So back here, we had the model was Q, and the solution was this. So actually, we've we're following this upper path, and we want to make this, we want to do this, and we analyze this model. And we start, once we do that, then we can calculate all the questions. We're going to answer all the questions if we can do that. Now, just like before, just like with the machines, so this is analogous to the two machines and the repairman with all those rates. Here we have all these rates. But here we have a nice situation that we can look at the process using Q as the number of customers in the system. Right? The number of customers in the system. That could be in service or it could be waiting. And we assume that if the barbers, which are the servers, if they're free, the customers will immediately go into service. And as soon as somebody finishes, if there's anybody waiting, they immediately go in. Okay, so then the question is what happens in the long run? And when we think of this, it's natural to have states 0, 1, 2, 3, 4, 5. Because there can be any number of people in the system from 0 to 5. If the system's full, if the 2 barbers are busy and the 3 waiting, there can be no more. They're going to be blocked. So there's only 6 states. 0, 1, 2, 3, 4, 5. Those are 6 states, right? Those are the possible states. And what we do is we make a state diagram showing the rates to all these states, just like we did with the machines. So if the system is empty, we think, well, how do we move here? If the system is empty, what can happen? If the system is empty, the only thing that can happen is there can be an arrival. And arrivals occur at rate lambda, and they take you here. And if if one person is in the system, what can happen? Well, there could be another arrival that takes you here. On the other hand, this one is in service and so can be served and will be occurring at this rate, because the service rate is mu for each individual server. So what you want to do is make this picture. The important observation, this picture is a lot easier than the machines, because when there's 0, you're only going to go to 1. Everything's continuous. You're going to only have one event at a time. All the random variables have densities. With probability 0, you're going to have 2 things happen at once. So only one thing's going to happen at a time. So if you're at 0, the only thing's going to happen is you're going to go to 1. And if you're at 1, you can either go back to 0 or up to 2, and so forth. And if you're at 2, you can go to 3 or back to 1. So you're here. Now things get interesting here is if you're at 2, both servers are working. So you have 2 servers working. Each of them are exponential service times. By the lack of memory property, it doesn't matter how long they've been working on those customers, because you're assuming they've got exponential distributions. So at any time, when there are both servers are busy, each one is going to finish at rate mu. And indeed, the minimum of the 2 exponential random variables is an exponential random variable with mean 1 over 2 mu. So this is going to be 2 mu, because 2 servers are busy, each at rate mu. And indeed, at this instant, at any time 2 servers are busy, the time until the next service completion is the minimum of 2 exponential random variables, which is exponential with rate 2 mu. Okay? Now, if 2 are busy, again, we can go to 3 again with lambda. And if it's 3, if there are 3 people there, only 2 are in service, so it doesn't change. So this is still 2 mu, because only 2 are in service, even if there are more there, and so on here. And you can't, when there's 5, you can't have any more, because they'll just be blocked. So this is the state diagram or rate diagram. We've done this rate diagram. Just like with the machines we talked about last time was more complicated because there was flows in different directions. Here, you either go up or down only. Is that something I should know about? Okay. So this particular variation of a continuous time Markov chain, it's a continuous time Markov chain. So we can make a Q matrix. And if we make a Q matrix, let's do so over here. If we make a Q matrix, that's what we're supposed to do. And we go from Q to 0 to 1 is lambda. Everything, and 1 to 2 is lambda, and this is mu. This is 2 mu lambda. If I get this to 4, 4 to 5 is lambda, and 2 mu, 2 mu, 2 mu. So we can go up. Everything else is 0. Now, on the diagonals, remember, is minus the row sums. So the diagonal is going to be, this is going to be minus lambda, and this is going to be minus mu plus lambda. By definition, in the Q matrix, the diagonal is the negative of the row sums. So when you're defining Q matrix, you're defining the off-diagonal elements directly. The off-diagonal elements are defined directly by this picture. Yeah?
What about the abandonment possibility?
Ah, we haven't got the abandonment yet. Thank you. Thank you. I just screwed up this example, didn't I? So we have to have the abandonment. Yes. Yeah. Good. Thank you. Thank you. That should have been deliberate. Hopefully many of you were unhappy. Or you just realized that he's an idiot and it's okay. Okay. So I forgot the abandonment. So indeed. So as soon as we get to 3, there actually could be abandoning, right? This guy who's sitting in the queue can be abandoning, which I forgot. So actually, the 2 mu, the 2 guys in service can complete at this, but the 1 guy abandoned can also rate at this. And he will be gone, and there'll be only, with rate theta, the guy in waiting will abandon and move you back down here. And here it'll be 2 theta, and here it'll be 3 theta. Right? Hopefully you were ahead of me and saw that already. So what did I do? I forgot about the abandonment, which is this stuff. But think about what's sitting in what's going on. Here we are in 4. Actually, when we sit here, we're at some time, and there are 4 people in the system. So there are 2 in service and 2 waiting. There are 4 people in the system. Actually, all 4 people could do something. The 2 in service could complete, or the 2 abandoning could abandon. So there's some rate at which all 4 are going to leave. Plus, somebody could arrive. So you could think of at this time, at any time when there are 4 customers in the system, right, there are actually 5 things, exponential clocks going on. There's a potential arrival, and there are these 4 possible departures, 2 for service completions and 2 for abandonment. You have going on 5 independent, at this point, 5 independent exponential clocks about what's going to happen next. And with rate lambda, it's an arrival, and with rate 2 mu plus 2 theta, it's a departure. And I should include the thetas, because I forgot them in the model. And you could make other features that would be similar. You could have you could change this lambda. Let's just think of, suppose somebody comes and they see that if they see they have to wait, half the people who see that they have to wait are just going to go away. If they have to wait at all, they're not going to wait. If they can't go in and receive their haircut immediately, they're going to leave, half the people. That's called balking. So what do we do then? Well, they get at 0, they get right in. 1, they get right in. But when there's 2 there, they don't get in. So half of them are going to leave. So the arrival rate's only half, right? Suppose half the people with arrival rate half, if they have to wait, will leave. So you would make this way, right? I've just added balking with probability 1/2. In other words, if you come and the system's full, if the servers are all busy and you arrive with probability a half, you'll just go away. So the arrival, you had originally a Poisson process and you split it into two independent Poisson processes, those who would leave and those who will stay and wait. So it's a new Poisson. Suppose they bulk with probability 1/3. That would be better to make it clear that this is. Okay, they bulk with probability 1/3, so they stay with probability 2/3. It's a new Poisson process then with this rate at those times. Everything is specified deterministically. They're all rates, but we're interpreting the model as stochastic. And we actually want to describe the implications of all the stochastic variability about these rates. So, I mean, first I had abandonments, but I forgot to include them here. And now I've added these bulking so that this changes. But it doesn't matter. There's 6 states, and there are a bunch of these lambdas and a bunch, there's a bunch of rates this way, and there's a bunch of rates here. And it doesn't matter too much. So if we change this, we should say, oh, I did this wrong. Now this is 2/3 lambda, 2/3 lambda, 2/3 lambda. And this is in 2 is this, but this is 3 plus theta plus 2 theta plus 3 theta, right? Just translating. So I should first of all do this right, and then I just put it directly in here. And then I have to do the diagonal corresponding. By adding these features, the flavor you should get is actually you can represent a fairly complex behavior here, because you can have this bulking captured just by adjusting these rates and these abandonments, and you can have 1 server or 2 server working. So you get quite a few features in this model by having these variations. And yet it's, in some sense, that model looks like the following version of the model would do. This is another variation of the same model. It's even more general. But it's a special, the other one there is a special case. Now, in this picture is the same as the other, except I've just written, in state 0, there is an arrival rate lambda 0. In state 1, there's an arrival rate lambda 1 and a service rate mu1, or this is a birth rate, birth, and death. So you go up by birth rates and down by death rates. This is a birth-death stochastic process. We go up by birth rates, down by death rates, and this is just a special case for specific birth rates and death rates that we got with this bulking and service and abandonment. So one point of this story is, well, this is just another example like those machines where you have all these things going on at rates and you make a stochastic model. That's the first part of the story. There are a lot of models, a lot of these queuing models that are like this, and the natural process you look at is the number of customers in the system, and it goes up 1 or down 1, so it's a birth and death process. So you have a picture that looks a state diagram like this, or in more generally like this, or it could there could be no upper bound, and it could be an infinite one of these, right? There could be no upper bound, it just goes on, but it's like this, and you translate it into a Q matrix, and you've made the model. And you can solve it by solving alpha Q equals 0. Okay, so this happens to be birth-death process where they go up 1 and down 1 all the time. So this is a very commonly occurring class of continuous time Markov chains. The good news is this class is much easier to solve than this general one. Here you're going to do alpha Q equals 0, which is a system of n equations and n unknowns. Here it's much easier. The solution is really easy, which we can think of in this context. Now, can I persuade you that this is easy? I want to persuade you that the solution to this is easy. Now, what do we mean by solution? So I guess part of the issue is what question do we want to ask? Okay, I mean, that's sort of one of the issues is what question do we want to ask has to do with what questions can we answer. So what can we do with this model? Just like in discrete time, we're thinking, oh, the model, we're going to specify the local behavior. We're saying at any given time you move from state to state in this random manner with these rates. What we want to know, we don't know right off the top of our heads, is what is the implications of that in the long run. So, what's the distribution in the long run that there'll be different numbers of people in the system? And then things like what fraction block, what fraction abandon, all this stuff. What happens in the long run? You run the system for a long run, long time. What is the fraction of things that happen? What fraction of people get served immediately? What fraction of time? What fraction of the customers are blocked? What fraction abandon? What's your average waiting time? And so forth. The whole description of what happens in the long run, where you say long run averages. All of that's going to come from solving alpha q equals 0, because you're going to find the long run probability of being in each of those states, and then you can compute everything. Okay, but in this case it's even easier. So we don't need the Q matrix directly. I mean, these entries are equivalent to the Q matrix, but with this picture, you can figure out what happens in the long run without directly writing down the Q matrix. And the idea is to think about what happens across one of these boundaries. So you make a cut here in this picture, and you imagine that you found alpha 0, alpha 1, alpha 5. These are the steady state probabilities. And we know these are found by this, but we don't know them yet. But imagine we found them, and we make some cut here. What we want to do is look at the rate of flow in steady state up this way or down this way. What is the rate of flow from 2 to 3 in the long run? And what is the flow from 3 to 2? And the thing that should be obvious, and it's true, that the flow this way has to equal the flow this way in the long run. I mean, that's the long run fraction of the number of, put it this way, the number of transitions from here has to differ from the number of transitions this way at any time by at most 1. Because you have to go back and forth. You can't jump. Remember, you're always going to the neighboring state. So at any time, the number of times you've gone this way can differ from the number of times you've gone that way by at most 1. So when you take the averages, they're going to be identical. Okay, over all time. What that means is if I look at alpha 2 times lambda 2 has to equal alpha 3 times mu 3. The rate up there is the long run probability of being here times this rate up. It's got to equal the probability of being here times this rate down. This is up and down. The probability of being at 2 times the rate up has to equal the probability of being at 3 times the rate down. We don't know the alphas yet, but whatever they are, they have to satisfy this equation. Which tells you that alpha 3 equals alpha 2 times lambda 2 over mu 3. Okay, let's I've sort of lost interest in Michael and Sean and the barbershop and have kind of abstracted it so that we've got this general birth-death process. But we've got, we end up with alpha 1 equals lambda 0 mu 1 alpha 0, alpha 2 equals lambda 1 mu 2 alpha 1, alpha 3 equals lambda 2 mu 3 alpha 2. In other words, I'm just writing this equation with cuts at each place. If I cut here, I'm going to get the first equation. If I cut here, I get the second equation, and so forth. So if I do this, I'm going to get lambda 1, mu 2, lambda 0, mu 1, alpha 0. And if I do this one, I'm going to get lambda 2, mu 3, lambda 1, mu 2, lambda 0, mu 1, alpha 0. Okay, this is the cut. This is the cut here. Alpha 1, mu 1 equals, I've just put it this way, and then this way. But originally, it would have been alpha 1, mu 1 equals alpha 0, lambda 0, the cut here. The next one's the cut here. The next one's the cut here, and so forth. So for each of these cuts, I get an equation. But I can solve them recursively. Alpha 1 is a constant times alpha 0. Alpha 2 is a constant times alpha 1, and therefore a constant times alpha 0. So I can write down all the probabilities as a function of 1. There's only one unknown, alpha 0. So when I want to know what these are, what is alpha 1? Alpha 1 is, alpha 1 is, the point I'm going to get to is I'm going to say alpha 0 plus alpha 1 plus alpha 5 equals 1. So I'm going to have all these recursive equations in terms of alpha 0, and then I'm going to sum this up and find the alpha 0. So this is going to be, if I write this down, I'm going to get alpha 0 plus lambda 0 over mu 1 alpha 0 plus lambda 1 mu 2 lambda 0 mu 1 alpha 0 plus, so I'm going to get alpha 0 equals 1 over 1 plus lambda 0 over mu 1 plus lambda 0 lambda 1 mu 1 mu 2 plus, and the last one is going to be so these terms are this ratio, the product of two ratios, the product, so successively. But all I'm doing is, the point is, you don't need to remember that answer. All I'm doing is at each cut, I get this simple equation like this, at each of these. And I write all those equations down, so I solve all of these in terms of alpha 0, and I just sum them up. And then I know all of alphas. I solve them all recursively. Once I do these cuts, I get each of these alphas in terms of the one before, and I sum them all up, and they have to be 1. So it's all recursive. So I don't have, instead of solving a system of equations, it's just recursive. So I don't need to remember what the form of the answer's got. This is the general form of the answer. You could memorize this. You could write it down on your sheet of paper. That's fine. But it's once you remember this picture that the flow, stationary flow up and down across between any two states has to be equal, then you can write such equation down and solve it. And so you reduce, instead of solving a system of n equations and n unknowns, you do it recursively. And that's because you can only move to neighboring states. You can only move up and down. So you can't, this story would not be correct if you could sit here and somehow jump somewhere. Well, as long as but this thing is you only can go this way. So the only way, you can't go from 5 down here. So when you look at this point, the only way you can cross this is from here, because you only go locally. And the only way you can go this way is from here. So you only need to consider these two states, because you can only move across this line from these two states. So that leads this. And therefore, you get an equation with one, in terms of one variable in terms of the other, and you reduce it, therefore, everything in terms of alpha 0. Well, and so there's an even broader interpretation, which will fit into the story of what we've done so far, is that this property we're doing here is really a form of reversibility in continuous time. We're actually solving the reversibility equation in continuous time. So what you would have wanted in continuous time, if you were to do that, if you were to think of reversibility, remember that we said something about pi I Pij equals pi j Pji. This was the discrete time Markov chain reversibility property. Stationary probability of I. This is the stationary flow from I to j, stationary flow from j to I. The reversibility equation in chapter 4. Here, this is the continuous analog. These are the stationary distributions. Flow from I to j equals flow from j to I. These are the steady state probabilities. These are the instantaneous rates. So this is saying flow from I to j equals flow from j to I for all ij. If this is true, if you can find, if your Q matrix has the property that you can find these alphas, then it's reversible in continuous time. And this alpha will satisfy this. So this local balance implies global balance, but not the other way around, just as before. But this is going to be true for birth-death, and in birth-death was just the equations we had written down. The equations we wrote down were like this. These individual equations are precisely this. Because the only way you can go to one state and another is I has to be I plus 1. You can either go down from here and up from here for any I. I mean, you could be going to I and I minus 1, but it's the same thing as this. So this equation that we were looking at here is just an instance of this local balance equation. The local balance, which is the continuous time analog of this reversibility local balance equation in discrete time. The most common occurrence is just what we just did. There's umpty-ump of these queuing models. They could have 2 servers or 7 servers. They could have 3 waiting spaces, 4 waiting spaces. You could have 4 computers in the lobby at downstairs. You could have 5, 3, whatever. And this model is, and everything being Markovian means that everything's defined deterministically in terms of rates, but you get this birth-death model, and that's really a big class of these models. So you get a whole lot of names. So in this context, we made this even, we had all this bulking and stuff. We had made it actually hard, but this, which is the same thing as, and which is the same thing as this. And then you'd have, and then we actually did something that was like this, and then we did something even more general with the bulking. This model is called the MM1 queue, the kind of most basic model, single server queue, infinite waiting room. So all the lambdas, music, everything, it's very simple. Here's S servers, and here's S servers and R extra waiting spaces. This is sort of the simplest model, slightly more complicated, and this is more complicated still, and then this thing with the abandonment's more complicated still, and these you could, and these models all have lots of analysis and explicit formulas, but it's fundamentally the main thing is this. They all fit this. So if you look in the book, there's a whole chapter on queuing theory. A lot of it will deal with this. And a lot of chapter 6 deals with this birth-death process model. That's the main, actually, the prototypical continuous time Markov chain, the simple natural application is a birth-death process. It's actually more likely, if you do a continuous time Markov chain, that you end up with a birth-death process than not. So reversibility is more common in continuous time. Okay, now this stuff, this reversibility goes well beyond birth-death processes because the process doesn't have to be one-dimensional. So this is where queuing networks comes in and so forth. This reversibility is very powerful for more complicated state spaces. But the point that follows from this is all birth and death processes are reversible. So the birth-death process, somewhere I had this continuous time Markov chains, birth-death. Actually, if I did, birth-death is a special case of reversible continuous time Markov chain, which is a special case of continuous time Markov chain. So this model is the one that you really, the centerpiece of a simple model. And then reversible continuous time Markov chains is a larger class in continuous time. And then this is alpha q equals 0. And solving this is this. And the theorems are roughly follow exactly like chapter 4. So if you go into section 4.8 of chapter 4, where we talked about reversibility and like that stuff about the graph and the night, all that stuff has analogs in continuous time. Well, let me now discuss. Let's return to the barbershop and think about questions that we might ask, and then what the answers would be. So the thought is we've got this problem, and we might think of various questions, and we'll think about the answers. So what we've done is we did some math. We recognize this is a birth-death, and we calculated these steady-state probabilities by the method I just imagine we did those already by the method I indicated. So we now know alpha 2 is the long-run fraction of time that there are two people in the system. And by our rules, they're both receiving service. Nobody waiting, two people there. Alpha 3, there are two there and one waiting. What's the long-run fraction of time that there are two there and one waiting is alpha 3. So we found those. We found the long-run fraction of time at which we're in each of those 6 states by solving for these 6 steady-state probabilities. So we might ask, and then we start asking other questions. So I just want to focus on what would those questions. So then if you say, well, what's the, what fraction of customers get blocked, don't get in? What fraction of customers get blocked? So then you think, well, when is a block going to occur? A block's going to occur when the system's full. So the fraction of customers that are blocked, the blocking probability is alpha 5. That's the fraction of time the system is full. Now there's a little bit of issue that you want to think that the arrivals are going to see the system in the same as, this is the long run fraction of time that the system is full. There's actually a little sophistication that the arrivals will see that what the arrivals see is the same as the long run average, which actually follows because of the Poisson process. So this is blocking probability. What's the expected number of customers in the system? So if we might use this for steady state, long run. The expected number of customers in the system, well, alpha, 0 times alpha 0 plus 1 times alpha 1 plus 2 times alpha 2, right? This is to say that most of these things are obvious, right? The expected number of customers in the system, these probabilities weighted by the numbers, right? Okay, so it's a little trivial. What's the, what is the fraction of time that what was the fraction of time that they're both busy? Say, well, what fraction of time are they simultaneously both busy? We say, oh, well, that's easy, that's, right? For all these states, they're all busy. Okay, so it's most things, well, when you look at last time, so there's an issue. If you look at the problems we discussed last time, they're on the web page. I didn't actually get to this part. There's the part of the systematic analysis. So this is typical of all these problems, right? There's part of the story that's very straightforward and systematic, but of course you got to know it. So that would be here, somehow you've got to solve alpha q equals 0. You got to make the Q matrix, that's the model. You got to solve alpha q equals 0 somehow. Alpha is the steady state distribution. That's most of the work. But then you're asked a bunch of dumb questions to interpret what that means. That's what I'm getting to now. So like in the business of going from Atlanta, the salesman going from Atlanta to Boston to Chicago and so forth, there's a question there at the end that says, what's the average number of trips from Atlanta to Boston per year? Okay, that isn't directly given to you, but the reasoning is not difficult with once you've solved once you found alpha, the reason's not hard, just like these questions. I mean, in some cases, they're a little tricky. So the point is, there's no end to those questions, right? So you kind of can't memorize like a robot how to think, right? If you know how to find alpha, you can think. All this stuff is not hard. But you want to prepare yourself in these examples to think, oh, the theory says understand how to construct Q, how to solve alpha Q equals 0 to find alpha, and then again, how to answer the questions given I know alpha. That's this kind of stuff. What is the blocking probability? What is this? And part of the questions in the book and in the homeworks and exams are some of each. Well, let's see. What other kinds of things would we have here? Things get a little harder, and we probably aren't going to go there if we ask questions about weighting. If we said, how long do you wait? What's the probability that you have to wait a certain amount? It's a little bit more complicated. So that's part of the theory. Certainly is covering that. So if we thought of, well, let's say we asked the question, what's the probability that you abandon, right? Let's ask that. That's just a cell phone. No problem with that, right? No problem. I can handle a cell phone. Okay, what's the probability that you abandon? Which is what you want to know right now. Okay, what's the probability that you abandon? Let's consider that. You're thinking that there you are. You're in line waiting to get a haircut. It's about 12:06, and you're the second person in line, and you're thinking it's about time for the secret word at this instant, and so it's time to abandon. Like you're going to all want to abandon now. So probability of abandonment, or abandonment probability. Okay, either way. What long-run fraction of customers that abandon? So you're thinking, well, you only abandon while you're waiting. So if there's 2 there, you don't abandon. But if there's 3 there, that's the probability. That's the fraction of times there's 3, and you abandon at this rate. Right? This is the abandonment. This is the abandonment rate. Now what I've just made is the abandonment rate. Let's be a little careful. That's the abandonment rate. This is the probabilities, the steady state probabilities of being in each of these states, and this is the abandonment rate. So this is the abandonment rate, and then if I divide that abandon that by the arrival rate. So this is the abandonment rate, and this is the arrival rate. So that's the long-run abandonment probability, is the abandonment rate divided by the arrival rate. What proportion of the arrivals abandoned is the total abandonment rate divided by the arrival rate. So this is this, whereas this is the abandonment rate. That's probably a good illustrative question. What is the abandonment rate when you asking that's not coming immediately out of alpha? It's not alpha it's not alpha 3 or something, right? But it's not hard. It makes sense. It's just once you understand what alpha is, answering these questions are pretty straightforward. Okay. It seems like it's getting to be time to abandon. We actually have a few minutes. You may have, if you have anything to discuss on this. It seems like, does anybody have anything to elaborate. I can elaborate. Maybe there's some residual point of confusion. Yes?
So I understand the abandonment probability with the lambda when there's a single lambda transition probability.
They're here.
Yeah, what happens in the general model?
Yeah, the general model, this would be, that's right. That would be harder. You would maybe think, then you actually, what's harder is what is the arrival rate? So your point is what would be the arrival rate, right? So good point. If this were, I'm thinking back here, and back here the arrival rate was lambda no matter what. If it wasn't that, it would be this. I mean, then there can't be any arrivals from state 5. This is conceptually the idea is the same. This is the abandonment rate divided by the arrival rate. What fraction of arrivals abandoned? This better be less than 1, right? Or we've got trouble. But I mean, that ought to be, that totally makes sense, right? Well, we need to define the arrival rate differently because it would depend on the state. And we could very well have this. A queuing model could be like this. In other words, the probability of joining might depend on the state of the system. So this lambdas could be state dependent. Might be very realistic. Might be much more realistic to say if they're going to bulk at different. If there's more people there, their abandonment rate's going to decline, say. Or maybe the real queue is the opposite. Right? The Russian queue. You have to validate. Do we have anybody want to validate this? Constantine had the idea that in the Soviet Union, that if there was a queue, people would rush to join it because there was surely something worthwhile there that you don't want to miss out, right? Like maybe all the good stuff arrived at the supermarket, and if there's a queue there, you want to join it, right? The bigger the queue, the more likely it is you want to join it, right? Okay, that's not crazy, right? It's not. I'm getting validation from the expert that this is not crazy. So these things actually might be increasing, right, rather than decreasing. Okay, just reality is something else. Actually, this point. So this last, whoever asked the question is going to, why did you ask the question? We'd have gotten out 5 minutes early if you had that say. Actually, one of the fascinating things is that, in these systems, humans are involved. And actually, the model isn't necessarily fixed, right? Our concept is the model is you introduce these parameters and they're given. The parameters could be increasing, decreasing, whatever the values you assign. But actually, what happens may be dynamic and behavioral response. If this is people, they may be adapting. So that's one of the interesting things to think about in these queues is whether, in fact, people are adjusting dynamically to what's happening. So your response might be conditioned on the level of the thing. If the service is, your response might be adaptive. In which case the model may not make sense without, because all the rates may change over time depending on what happens, which is a kind of interesting thing. Okay, that seems to be. Is somebody else? If you have that was a good question. These questions, especially good, like the one about what about the abandonment to begin with, was a major help in thing. But if that was, thank you. But anyway. No more, that's enough? Okay, lunch then. Okay, let's move on to lunch. I got home, I've collected homework.